Okay, so we're going to start by looking at sequences, and today, friends, we're going to be looking at recursive rules. The textbook definition of a sequence is a function whose domain is a set of consecutive integers, and what that means is that it ends up being like this list of numbers with separations in between it. So you know how like if we plot points on a line, like if something's linear, they're all the points in between that line. If it's a function instead, like there's a point for one, a point for another, and then a point, etc., which kind of is that list of numbers. So when we talk about a finite sequence is something with a limited number of terms. So something like 4, 8, 12, 16, then stop like that, okay? So that's a finite sequence. And if something is infinite, what does that mean? And it's unlimited, right? So basically, if it's infinite, it continues forever. So the way that you denote that a sequence is infinite is you just put a little dot, dot, dot at the end, and then that says it's going to keep going, okay? Now, in the warm-up, we looked at a couple different things. One of them is that if it was a linear thing, and that's going to be called an arithmetic sequence. If we end up seeing an arithmetic sequence, what that means is that the difference of consecutive terms, and that just means the terms right after each other, is constant. Okay. And again, one thing we noticed about that is that that looked linear. So in an arithmetic sequence, we're adding or subtracting the same thing. And in an arithmetic sequence, we're going to say that D is called our common difference. And to find our common difference, we always take the new minus the previous. And so let's contrast that with a geometric sequence. If we have something that's a geometric sequence, instead, we say that the ratio of consecutive terms is constant. And when we talk about the ratio, that's when we're dividing terms. So geometric sequences look exponential because we're going to be multiplying. And we're going to call R this common ratio. So in the common difference, we find that by taking, I'll just write that here, the new term minus the previous term. And in a common ratio, you find that by taking the new term divided by the previous term. You can squeeze that in. Okay. And so, and then there are some sequences that have a pattern, but aren't arithmetic. We're not adding, subtracting, or not geometric. Okay. So let's decide if the sequence is arithmetic, geometric, or neither. If it's arithmetic, we'll find the common difference, and if it's geometric, we'll find the common ratio. All right, so let's take a look at these. In letter A, we have 4, -8, 16, -32. That follows a pattern, right? What pattern does it follow? What do we do to get from one term to the next? What are we doing? Multiplying by -2. Is that always the case? Yes. So because we're for this sequence, this is always the case. So does that mean that this is arithmetic or geometric? Geometric. Good. Okay. So this is going to be geometric. And that means that there's going to be an R value, a common ratio. The common ratio is what you're doing to get to each term. again, you can also take the new term divided by the previous term. Do you notice that if you take -8 divided by 4, that's the same as 16 over -8, which is the same as -32 over 16. And in all of those cases, what is that? -2, okay? So again, I don't need to see this work here unless it's not something that's evident. But notice that the number that you're multiplying by ends up being the common ratio when it's geometric. Okay, what about letter B? 5, 11, 17, 23, 29. That seems to have a pattern. What's happening to get from one term to the next here? Adding 6. And is that true in every single case in this sequence? Yes. So because we're adding the same thing, what does that mean? Good. Yes. And so that's an interesting thing, you guys. So I look at that word and I know my instinct is to say arithmetic. So arithmetic is the noun, like what we studied in school. Arithmetic is the adjective describing the sequence. So you know how in the English language sometimes you pronounce things differently? That's kind of what this is. So when we call these, so what you studied in grade school is called arithmetic. When we describe this type of sequence, it's arithmetic. So since it's arithmetic, there's going to be a common difference. What do you think the common difference is going to be? 6. Perfect. And again, if you took 11 minus 5, that would be the same as 17 minus 11, etc. Okay, all of those are the common difference. Now, in example C, what about this one? What are we doing to get from one term to the next? Well, we multiply by 3 and then by -3 and then by 3 and then by -3. Is that the same? No. So even though there's a pattern and there's multiplication involved, this is neither arithmetic nor geometric because it doesn't have the same ratio. So, right, it's not constant. Perfect. Okay, so there's a pattern, but it's not a constant ratio. Okay, so I want you guys to try A through C. You try A through C. See if you guys can figure those out. Okay, we've had a little time. What'd you guys have for letter A? Neither. Now it starts out looking pretty arithmetic, right? But do you see that this isn't consistent? We're adding 4, adding 4, adding 2. That's not a consistent pattern throughout. So that's a neither. Okay. How about letter B? Which is this one? Good. Geometric. And what would you say that R then the common ratio is? 1/3. Good. Okay, excellent. And how about letter C? Arithmetic. There you go. Nice. And for this one, what is the value of D? -6. Perfect. Okay. How are we doing on arithmetic or geometric? Feeling okay with that? Great. Okay, so the thing is that sometimes there are rules that are defined what's called recursively. And if we have a recursive rule is kind of like the number 3 from our warm-up, but it doesn't have to be. A recursive rule tells how A sub n, and A sub n is representing like your next term. So it tells how A sub n, your term, is related to one or more previous terms. And there are 2 parts to a recursive rule. The first thing is going to be the first term or the first terms. Because if it's related to the previous terms, we have to know where to start. okay? And then the second part of the recursive rule is the rule itself, okay? And in the textbook that we're using, they use A, and then as a subscript is n minus 1, okay? So it's not A times n minus 1, there's A, and then as a little subscript, there's n minus 1. So when we see this, this represents the value of the previous term. So again, A sub n is the term that we're currently like wanting or looking at, and A sub n minus 1 is the value of the previous term. So let's write these, the first 5 terms of the sequence, and notice that these are defined recursively. Notice that in number 2A, there are 2 parts. It's telling you where to start, and it's giving you the rule. So notice that this is telling us that in order to get this term, I'm going to take the previous term and add 4. That's what that A sub n minus 1 means, what the previous term is, okay? So it tells me A sub 0. So what that means is that to get A sub 1, and I'm not going to write these for all of them, but just as we get used to it, to get A sub 1, I'm going to write the previous term. So before A sub 1 would be A sub 0, and I would add 4, okay? To get A sub 2, I would take the previous term, which is A sub 1, and I would add 4. What would I do to get A sub 3? A sub 2 and add 4, okay? And then what about to get A sub 4? A sub 3 and add 4, okay? Now I'm gonna stop because that's gonna give me 5 terms. Now I know I've only listed 4, but didn't they give me 1 to start with? So 1, 2, 3, 4, 5. Now let's say that I wanted to find A sub 4 right now. I need A sub 3 plus 4. Do we know what A sub 3 is right now? No. So in a recursive rule, one of the issues is that we have to start from the beginning and go forward. So let's actually do that. What did they tell us that A sub 0 was? 1. So I'm going to take 1 plus 4, so that's going to be 5. Okay. Now I know A sub 1. A sub 1 is 5. I'm going to add 4, so I get 9. Now I know A sub 2, which is 9. I'm going to add 4 to get 13. I know A sub 3, that's 13. I'm going to add 4 to get 17. Now, when we write a sequence, it's best practice to write it as they were in our other examples. Do you see how they're listed with commas in between? So that's how we're going to write our final answer. We're going to start with the first term they gave us, God bless you, 1, and then 5, 9, 13, 17, okay? So that's the gist in how recursive sequences work, okay? Now, I don't need us to write all of that every time for these easier ones. This is telling me in this question that I have A sub 1 telling me where to start. And here, do you see that it's telling me that I'm going to multiply 3 times the value of the previous term? So to get A sub 2, essentially, I'm going to multiply 3 by A sub 1. What was the value of A sub 1 in this problem? 1. Okay, so that means that that's going to give me 3. To get A sub 3, I'm going to multiply 3 by the value of the previous term, which was 3, and that gives me 9. Now, without doing any work, what's the next term gonna be? 27. And what about the next term? 81, okay? So I don't need, when they're very obvious, I don't need to see like all the work that we did here, but I wanted to make sure you understood what the recursive sequences were really doing, okay? So let's write what these are: 1, 3, 9, 27, 81. Okay. And again, when the pattern is easy to follow, we don't necessarily need any work. Yeah. It's just whatever came after this first one. So this one started with 0, and so 1 was next. This one started with 1, so 2 is next. Okay. Now in this one, I want us to look at this. We have 2 terms that are given, and the reason is because this rule right here is taking a sub n minus 1, which is the previous term. What do you think a sub n minus 2 means? If a sub n minus 1 is the previous term, what's a sub n minus 2? The one that's 2 terms before, right? So I call that the previous term. It's not an official name, okay? But if a sub n minus 1 is 1 before, a sub n minus 2 is 2 before, okay? So this is saying that to get, then notice that I have a sub 1 and a sub 2. So what would the next one be? That would be a sub 3. So I'm going to take the previous term, which was a sub 2. What's the value of the previous term? 4. And I'm going to subtract the term before that, which it says was 1. So a sub 3 is 3. Okay. Now to get a sub 4, again, I want the previous term. Yeah, Charlotte, go ahead. Yeah. Oh, so it's the whole a sub n minus 2, so not the n. So what this is really saying to find a sub 3 is that the previous term would be a sub 2. The previous would be 2 terms before a sub 3, which would actually be a sub 1. Does that make more sense? Okay. Yeah, sure. Okay, good. Thanks for clarifying. So to find a sub 4, I'm going to need to take the previous term, which is a sub 3, which happens to be 3. And now I want to subtract the previous term, which was 4. Good, guys. So that gives me -1. Now I have a sub 5. What am I going to do to find a sub 5? -1, and then minus, I think I heard it, 3. Good, guys. And which is -4. Now again, I'm done because I was given 2 terms. I found 3 more. Isn't that 5 total? So I'm going to list 1, 4, 3, -1, 4 as the first 5 terms. Huh? Wonderful. All right, so let's talk about specific recursive rules when we have arithmetic or geometric sequences. Do any of these look arithmetic to you? Any of these patterns that we saw? Only one of them, just A, okay? Now A looks geometric, so, or sorry, arithmetic, my bad. So what we're gonna do is we're gonna define a sub 1, and then recursively what we do is we take the previous term and we're always adding the same thing to it. So we're going to, in this case, add D to it. And I have those 2 parts there on purpose. We have to define where to start, and then we have our rule. Do any of these look geometric? Kaylin? Okay, yes, B, all right. And in letter B, we're starting with a specific number, and we were always multiplying by the same thing, correct? So instead of a sub n minus 1 times r, doesn't it make sense to have like a coefficient in front of it? So usually we write it as r times a sub n minus 1. So we're multiplying by r. So in example 3, let's use these rules to write a recursive rule for the sequence. So letter A. First, let's determine what type it is. Does this look like this is arithmetic, geometric, or neither? Good. This looks like this is arithmetic. And when it's arithmetic, what's the common difference? 10. Good. Okay. So the rule recursively, which again always deals with the previous term, is going to be a sub 1 equals, and we need to tell it where to start. What was the value of a sub 1? 3. That's what we're going to define. A sub 1 is our 3. We're going to start at 3, and now to get the next term, we're going to take the previous term, a sub n minus 1, and do what to it? Add 10 each time. Good. Okay. Now, how about letter B? In letter B, this one might not be quite as intuitive. Are we adding the same thing though? No. So let's check to see if we're dividing. Let's take 40 divided by 16. What do you get when we divide 40 by 16? 2.5. Let's take 100 divided by 4. What do we get? What is it? Oh, sorry, divided by 40, my bad. That would be 2.5. Sorry. What about 250 divided by 100? 2.5. What are we seeing in this case? A pattern. So what kind of sequence is this? This is geometric. And even though R wasn't obvious at first, what did we just find that R was? 2.5. So our rule is going to be a sub 1 equals, and where does it want us to start? 16. And now to find the next term, I'm going to multiply the previous term by 2.5. So 2.5 times a sub n minus 1. Okay. Great. All right, so now I'd like you guys to take what we did in examples 3. Which ones? Oh, yeah, take what we did in examples 2 and 3 and see if you can do, you try D, E, F, and G. All right, so here's what I got for you try D. 3, -4, -11, -18, -25. You good with that? Did we all write it out like this as a sequence? Okay. Letter E, 162, 81, 40.5, 20.25, 10.125, or you could have 40 and a half, 20 and a fourth, 10 and an eighth. That's fine. Okay, good with that? How about the next few tries where we write recursive rules? This was geometric. So in addition to having the rule a sub n equals 7 times a sub n minus 1, did you have the a sub 1 where to start? Do you guys see that if I don't have that a sub 1 there, I wouldn't know where to start? Like you wouldn't know what the first term was. So that's why that's very important to have. And then letter G, we were adding 11 each time, starting with 11. Are we feeling okay with that? Okay. Yeah. Oh, the a sub n minus 1, remember that this thing right here represents the value of the previous term. Okay, so that a sub n minus 1 is saying that's the value of the term that came first. Does that make sense? Okay. All right, so now let's look at this. If I look at letter A in example 4, this is not arithmetic. It's not geometric. But are you able to find a pattern in what to do to get from one term to the next? What are we seeing we have to do? What'd you say, Nolan? Add these two to get the next one. You guys agreeing with that? Okay. So what that means, I'm going to start on this, like the second line. So that means I'm not just going to use the previous term. The previous term was a sub n minus 1. I also have to use the previous term, which if this is a sub n minus 1, this one is a sub n minus 2, okay? And what did I do to each of those? I added them together. Now I'm not going to have the cloud yet because I have to define where to start. If I just said a sub 1 equals 1, would that be enough information for someone to complete this question? What else would they need? They do need a sub 2 equals 1 as well, okay? So because I'm using not just the previous term, but also the previous term, I need to make sure to define both of those, okay? How about letter B? This is not arithmetic, it's not geometric, but there is a pattern. How did we get 9? We multiplied by 3. Do we get 81 the same way? No. But what did we do to get 81? We square the 9. How do you think maybe we get 65, 61? Square the 81, let's check. Okay, let's try 81 squared. Oh my goodness, okay, we got it. So let's go back to that. And so aren't we squaring the previous term? Okay, so what we see here is that we're squaring the previous term. So to get my a sub n, I'm going to take the previous term, which is a sub n minus 1, and do what to it? Square it. That's the rule. What else, though, do I need to follow this rule? Where to start? Where am I starting? A sub 1 equals 3. Okay. Can you guys find the pattern in the next one? What does it look like we're doing here? Anyone see it? Oh, I'm hearing it. Multiplying. Do you guys see how we're taking these and multiplying to get this? Taking these and multiplying to get this? These and multiplying to get this? So my rule, I'm going to have to take not just the previous term, but also the previous term. And what am I doing to those two things? Multiplying them together. So what else do I need to define for this? That a sub 1, is that enough? And we need a sub 2. Awesome. Okay. So those are not arithmetic or geometric, but we could still write a pattern with them, right? Let's look at one last example, example 5. It says an online music store initially has 50,000 annual members. Each year it loses 20% of its current members, but it adds 5,000 new members. Let's write a recursive rule of the number of members at the start of the nth year. So if it loses 20%, how much does it keep? 80%. Okay. So our A sub 1 is going to be what? What would our A sub 1 be defined as? Where did it start? 50,000. It initially has 50,000 members. Okay. Now, each year, it's going to keep 80% of its current members. So I'm going to keep 80% of the A sub n minus 1. Again, that's of the previous year, okay? But then something else happens too. What else happens? We also add 5,000. So this is like a combination of the two, right? It's not arithmetic, it's not geometric, but it has kind of some pieces of both. So let's find the number of members at the start of the 5th year. Here's where we can use our calculator to kind of help us out. What we're going to do is enter A sub 1 in calc and then press enter. Okay. Then we're going to enter the A sub n expression in calc. But I want us to use that answer key for the A sub n minus 1. Okay. So in our calculator, we're going to put 50,000 and then press enter. We good with that? Okay. Now we're going to use the expression. The expression is 0.80, and then wasn't it times A sub n minus 1? I want us to hit second negative to put answer there, and then plus 5,000. Isn't that the expression that we came up with? That's A sub 2, right? Now just press enter again. A sub 3, A sub 4, A sub 5. Isn't that a lot easier than having to type it over and over and over and over again? So what we do is we keep pressing enter. And then in letters, so our value in letter B, our A sub 5 is 35,240. Okay. Now in letter C, it asks us to describe what happens to the number of members over time. Here you guys just keep pressing enter. And if we keep pressing enter, notice that it's getting smaller and smaller, but it's never quite getting to what number? True, even not that. Do you guys see that as I keep pressing enter and I get close to 25,000? So that's what we end up with there, is that you keep pressing enter and then you can see that over time it approaches 25,000. Okay. If you need a calculator to take home, let me know.